In this experiment, we will look at the overall heat of formation of certain metal oxides, and this will involve the measurement via calorimetry of specific steps involved in the overall reaction. And specifically, those steps will be the oxidation of the metal to its cation form, and also the reaction of the metal oxide with acid so that we can investigate the heat involved in the metal oxide reaction. In thinking about calorimetry, it will be helpful to first just discuss some of the principles involved in this experiment kind of conceptually. So we will be looking at a made-up reaction of A plus B makes C. A plus B makes C has a specific heat enthalpy change associated with it. And remember, enthalpy is essentially the same thing as heat change in the reaction. And we can have a positive value of delta H, which would indicate that heat is absorbed by the reaction. We could also have a negative value of delta H, and that would indicate that heat is released by the reaction. If heat is absorbed, it would be absorbed from the surroundings by the reaction. And that would mean that your solution that the reaction is occurring in would become colder, and also the container walls would take heat in from the exterior in that process. If heat was released, however, the reaction would actually pass heat to the water and to the container walls. So we can think about the overall heat transfer involving the water or the solvent and the container walls. And both of these summed up would be considered the surroundings of the reaction. So the heat in the reaction, Q reaction, is the negative, because whatever happens to the reaction, like if heat is absorbed at a positive value, then it must have been taken away from the surroundings. So the negative value is to show that whatever happens to the reaction is the opposite that happened to the surroundings. We have the Q of the bath, or the solution. We can call it Q bath. And we have the heat of the calorimeter, or the container. So I'm going to call that Q cal. So the heat of the reaction is equal to the negative of these two components of the surroundings. All right, so conceptually, that is how we will think about what is happening in our coffee cups. But we will be measuring the heat of these reactions in styrofoam coffee cups, and we chose this as our container for the calorimeter because it's an insulator, but it's not perfect. So some heat will be lost, and that is what this QCal term is there for. It's like the error of the styrofoam coffee cup. Even with 2 coffee cups, we will still lose some heat. All right, we will use a known mass of water for our bath, and we will measure the change in temperature of the water, which will, essentially be the change in temperature of our overall solution, and indicate the change in temperature of the reaction in essence. We will use a known mass of reactants, and a lot of times you'll see RXN to summarize the reaction. So QRXN is the reactants involved. Okay. We will also measure the change in temperature using a thermometer inserted into the solution through the lid of the coffee cup. And if we were to kind of reframe our original equation of Q reaction equals negative Q bath plus Q cal, it would look like this, where Q of reaction is equal to the negative of the mass of the water in the solution times the specific heat of water, because every substance has a specific ability to change temperature in proportion to the heat applied to it, and times the change in the temperature, which we will measure, Plus, our other term for the calorimeter will use the heat capacity of the calorimeter times the change in temperature. And so that heat capacity kind of takes into account the error of, the poor insulation properties of that calorimeter coffee cup system. So this is actually how we will calculate the value of the heat of the reaction. Now, because this is not taking into account the number of moles of reaction involved, it's not quite to the point of being an enthalpy, a standard enthalpy. If we divide by N, the number of moles of reaction, then that would give us our delta H naught that we can use later on in calculating our overall enthalpy of the total reaction. Okay, so some important details before we're able to actually get to the point of measuring the heat of the reaction is that we need to be able to quantify that error involved in the coffee cup system. And so we have kind of a calibration step that we will go through first to get the heat capacity of our calorimeter. And no two coffee cups are the same. You have different masses of styrofoam, minor fluctuations in the processing and manufacturing of coffee cups. We will be double layering them, but also maybe some of the lids are not cut to the same size and so on. The hole for the thermometer is not perfect. Heat will be lost, and it will be different for every group's calorimeters. But the strategy we will use is to mix a known amount and temperature of two different water solutions. So we'll have a cold water solution and a hot water solution. And when we mix them together, heat from the hot water solution will pass to the cold water solution, but some of that heat will also pass to the walls of the calorimeter. And so in a similar kind of equation, we could say that the Q of the heat of the hot water is equal to the negative of the heat of the cold water plus the heat of the calorimeter. So I'm going to say Q cold and Q cal. All right, so putting that into actual measurable values, we have MC delta T hot, so the mass of the hot water times the specific heat of water times the change in temperature of the hot water is equal to the negative of MC delta T cold. So the mass of the cold water, of course, the specific heat of water is the same. The change in temperature of the cold water would be different because we would be starting from cold and going up to whatever final temperature, whereas the hot water would be starting out at a higher temperature and going down to the final temperature. And then our Qcal term will just be Ccal and delta T cold, because we're going to treat it as though the cold water is our bath, basically. All right, so just to illustrate how you could get these values for delta T hot and cold, it'll be final minus whatever the initial temperature of that solution was. So if we're looking at the hot water, it would be the initial hot temperature. If we're looking at the cold water, it would be the initial cold water. And if you think about it, the temperature of the hot water is decreasing, so our delta T should be negative. Temperature of the cold water is increasing, so our delta T should be positive. And hopefully that will help all of your Ccal values to come out to a positive number, not a negative number. Okay, the last kind of component of this experiment is to apply our measurements to a conceptual understanding of the overall heat of a formation reaction. And so Hess's law states that the heat of the overall process is the sum of elementary steps involved in that process. So if we're looking for the overall enthalpy of a reaction, and we know the enthalpies of multiple steps that can be added together according to whatever proportions to get the overall, we can use that strategy. So in our case, we will be measuring the heat of a reaction, essentially taking a metal, which we're just using iron for this illustration, and this is the example also given in the protocol background. Iron being oxidized to iron 3+, which is found in our FeCl3 compound. And we are also measuring the enthalpy of when we take Fe2O3, or our metal oxide, and we react it with acid to get it back to this just Fe3+, which is in the form of FeCl3. Since the reaction that we're actually measuring in our calorimeter is the reverse of this, we'll have to take the negative value of whatever we have measured to apply it in such a way. You might notice that the way these two measured reactions are set up, Fe3+ will cancel out, and we'll get Fe makes Fe2O3 as the leftovers. And that is what we're shooting for in our overall reaction. We want iron plus oxygen makes iron oxide. And so the last part that we are missing in this overall process would be basically the formation of water. And that is because we want to take oxygen out of its elemental state and get it into a -2 oxidation state so that it can be used in this formation of Fe2O3. So that last part we are not actually measuring in the experiment. We can use a literature value for the delta H naught of this reaction to kind of add in to get our total value. So basically, after we have all three values of enthalpies for elementary steps collected, we can add them together to get a total value, and that will be part of the analysis involved at the end of the experiment and also in your report. Now, each group is going to be looking at a different metal oxidation process and conducting the first the calibration step, then actually measuring the oxidation of Fe reaction. So you'll just put iron, well, whatever metal you've used, with that appropriate acid concentration and measure the heat evolved from that. Then you'll take the metal oxide and add it to an acid solution and measure the heat of that. And this formation of Fe2O3 that we'll use here, or metal oxide, is really the reverse value of our reaction with HCl. So that's just an important thing to remember. You'll be given a value or able to look it up at least for the oxidation of hydrogen